the mass before plus Mn, which is the mass of one neutron, and the whole multiplied by c squared. This is equation 3.26 in Crane. You remember that I uploaded chapters 1, 2 and 3. I have also given them to the photocopier. You can take a printout from there, and it will be given to you at the price of the photocopy, okay, not at the price of the print. Okay. So, that will be convenient for you to study. Also, I told you that chapter 1 was just 2-3 pages, just the basic definitions, and I gave you that as a homework last week just to go through them. Chapter 2 is just a summary of some quantum formulas. Do not be scared of that. Whenever we use it, we explain it. And this is chapter 3. So, chapter 3 is about the properties of the nucleus itself. Like I told you, in order to understand nuclear physics, we have to understand the nucleus. Okay. So, that is what we are doing right now. So, any equation that I am using, I am also writing the reference. You can go and check it. Okay. So, can you please just take a picture? Okay. 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 Now, just as we discussed the neutron separation energy, we also have a proton separation energy. This is the symbol with the subscript P for proton. So, the equation is also similar. You subtract the two binding energies. A minus 1, Z minus 1 and N. And this will then be equal to the masses plus the mass of H1, and the whole equation multiplied by c squared. Now, this is equation 3.27 again from Crane. What is H1? Proton. H1 is actually hydrogen, but the mass of a hydrogen can be considered as the mass of the proton, because a standard hydrogen has only one proton, it has no neutron. And remember, we are only talking about the nucleus, we are not talking about the electrons outside. Okay. So, hydrogen mass has been taken as the proton mass. Okay, so far so good. Now, I would like to switch it on and show you a figure. So, the figure in this case will be, let us see, page 67. No. Okay, when you look at page 67, you do not have the book with you right now, right? So, maybe I will show you in a while. Okay. So, this is a diagram, a graph that shows that is known as the binding energy curve. Okay, so I will show you just in a while. Meanwhile, I will also explain another formula that's used for finding the binding energy. So this was one way of finding the binding energy. There is another formula that is known as the semi-empirical binding energy formula. Okay, so this formula, like in science, for example, one quantity can be calculated by many different ways for validation purposes, right. So one is the simple formula that we just discussed before, and this is another formula that's used, and this is known as the semi-empirical mass formula. In some books it is also called the semi-empirical binding energy formula, because if you multiply the mass by c squared you will get the energy, right. So this is written as you remember what capital A means and what capital Z means, right? Yes. So that's the same, and we will explain the other symbols. So there is a model in nuclear physics that's known as the liquid drop model. So this formula is based on that model. So liquid drop, you know what a liquid drop is, right. So this model treats the nucleons as if they were atoms in a drop of a liquid, and it is called semi-empirical because each of the terms is associated with a physical concept. Each of these terms is associated with a physical concept that we are just going to explain. Okay. So the first term. So how many minutes is this? Okay, good, great. Just don't forget, okay? Right. Okay, so first term. The first term is AVA. This is called the volume term. And it represents proportionality. Proportionality between binding energy and A and the volume of the nucleus. Okay. So this term, the subscript V is for volume, okay, and this capital A, as you remember, is the mass number, and this multiplied by A shows that the binding energy is proportional to capital A, and this is proportional to the volume of the nucleus. Okay. Now the second term. So the second term contains A raised to the power 2 over 3. So A, small a subscript s multiplied by A raised to the power 2 over 3. So this is called the surface term. S for surface, right? V for volume. So this accounts for the fact that nucleons On the surface of the nucleus,